This tutorial will introduce the bending force in Kangaroo in order to simulate the uncurling of material as a chain of springs attempts to find an equilibrium between one another in order to distribute the average curvature of the springs. So in order to do that, we need to work with some of Grasshopper's data structure components because the Kangaroo bend component requires a reasonably finicky set of inputs in order for it to work. Now the desired effect of all this is that we can begin to simulate how real-world material might perform. So the work by artists like Carlo Bora, as you see here, is working with similar types of material performance. So these strips of aluminium are curled into these shapes where the aluminium is essentially in a state of equilibrium. It's not trying to bend into another shape. It's simply pinned at either end, and this is the form that it takes. So we're trying to work with a similar logic. So I've got a polyline which I've made in Rhino. It's in 3 dimensions and it is curving unevenly. So the angle between all of these springs varies from spring to spring. So we're going to reference that into Rhino, no, into Grasshopper, sorry, and explode to get all of the different segments, cast it to a line just as we've been doing. Also get the endpoints, which we're going to pin in our simulation, and we can convert these segments into springs, which is again what we're doing almost all the time when we're working with Kangaroo. We want to allow them to maintain the same rest length and connect that up to a Kangaroo physics component. So we're going to pin the endpoints. Our geometry can be all of these lines. We need a toggle and a timer. And this gives us our basic setup to start adding other forces in Kangaroo. So we're going to have a look at this bend force. So it requires 3 points, which all have to have exactly the same data structure. So the points coming into these components need to be in the same branches. We have a bend strength parameter and a rest angle. So if we set the rest angle to 0, that's going to simulate a kind of an uncurling of this polyline. Now we need to define these 3 points in order to tell Kangaroo what the bend angle is going to be. So in other words, what we want to do is for each point on this polyline, say this point here, we want to find the next point on the polyline and the previous point on the polyline, and those will become our 3 points to reduce this angle here between these 2 springs. So we've got a bit of an issue because for the very first point on the polyline, we don't have a previous point, and the same goes for the end point of the polyline. So we need to reorganize our data structure a little bit so that we're not trying to create bend forces for the start and end points of the polyline. So we can work with our exploded curve, which gives us a list of all of the vertices, and we're just going to use a couple of shift list components to organize this data structure so that we get rid of the start and the end points. So let's hide everything and try shifting this list by 2 chunks of data. And that'll get rid of the first 2 points. So this point here, or this list of points, is going to form our point 3 in the bend angle. Okay, so this will be point 1, point 2, point 3, and that'll be our first bend force. Then this will be point 1, point 2, point 3, and that'll be our second bend force. So in other words, for these first 2 points on the curve, there's never going to be a point 3 because we don't have enough earlier points in order to create the other parameters for the bend component. Okay, so that's our point 3. Now we can shift it in the opposite direction, so by -2, and that'll get rid of the end 2 points. So this is going to be our point 1. So again, as we run along this polyline, this will be our point 1 of the final bend force that we're going to create, and then we'll have our point 2 and our point 3. But these 2 points can't be point 1, again, because we run out of data and we won't be able to provide all the parameters for this bend force. So lastly, we need to create this point 2, which means we want to get rid of the first point and the last point. So again, we can just use 2 shift lists. So we're going to shift by 1 and then shift by -1. And that will get rid of the start and the end points. Okay, so we got point 3, point 2, point 1, and that'll create all of our bend forces. So they get dropped into the force objects along with the springs. And now we should be able to run our simulation. And we'll hopefully see this curve beginning to uncurl. So the angle between these 2 springs, all the way along the curve, is tending towards 0, while the spring is trying to maintain its original rest length. So we should iteratively reduce the curvature along this spring. So this is working entirely with a polyline of springs. If we want to begin playing around with bending forces whilst attempting to simulate the behaviour of a surface, then we need to use a different component, and that is the hinge force. So I'm going to load up a example with some hinges. So we've got 2 meshes here. And we'll use this to start playing around with the hinge force. Now, in order to do this, we're going to be working with Starling as well as Weaverbird. So make sure you have the Starling plugin from Food for Rhino. The interesting thing about Starling is it gives us access to a whole bunch of mesh topology components. In other words, lots of useful components for describing which faces are connected to which other faces, which is exactly what we need for the kangaroo hinge force. So first of all, we need to convert these meshes into springs. So we're going to grab a mesh, make sure it's all welded, grab the edges, make sure they're lines, convert them into springs, maintain their rest length. Set up our spring physics component. Reference in some anchor points, and in this case I'll just use the corner points of the mesh, so that we'll be able to move these around and watch our mesh unfold. We can use our mesh as the geometry. And a timer to update the simulation. So this is our base setup, ready to go. And next we need to work out how to create these hinges between faces in our mesh. So to do that, as mentioned before, we're going to use Starling. Now Starling works, interestingly enough, mostly with polylines. So we need to extract the face boundaries of our mesh before we start working with Starling. Then we have these components called alchemists. Have no idea why they're called that. And one of them is called the adjacent faces component, and this gives us a data tree of all of the connected faces in the mesh. Very useful component. So if we connect up our face polylines, this component is going to run through all of those polylines and figure out which is connected to which. So each branch in this data tree is referring to a face, and then the data on those branches is referring to the index of the neighbouring faces. Now all of this is important because if we look at the kangaroo hinge force, where are we? Hinge, hinge, hinge. Similar to the bending force, we need to provide a whole bunch of points. So we need to have points describing the shared edge and points describing the tips of the triangles. So in other words, if we want to bend around this edge or hinge around this edge, we need to know this point and this point and this point and this point. Now if you created all of your mesh faces in a grid, this might not be so trivial, or it might be trivial, but if you're using a more complex mesh that you've modeled in some other program, then the faces are never organized into nice neat lists like this, and you need to use components like this adjacent faces component to build a map of the connectivity data between faces. So we're also going to use some sets components in order to be a little bit clever about how we find these triangle points and the shared points between faces. So what we're going to do is pull out these neighbouring faces from our list of faces and use some sets components to find the shared or unshared vertices. So use a list item to list these neighbouring faces from the list of total faces. And what we also need to do is, in order to work with these sets components, is create a matching list of the original face. So I'm going to measure how many shared faces there are for each face. So for example, this face here is only going to have one neighbour, but this face here is going to have two neighbours. And then we're going to use a duplicate data component to duplicate each face in this list this many times. Now the thing is, we need to make sure these data trees match up. So I've got a one-dimensional data tree which is telling me how many neighbouring faces there are, and I'm just going to graft the data tree, the list of faces, so that we have exactly the same data tree of faces. So we should have 19 branches, so each branch is referring to each face in the mesh, and over here we also have 19 branches referring to each face in the mesh. So we should be able to use that to create this many duplicates of each face. So we have two perfectly matching lists. I'm just going to simplify both of them. So now we have a one-dimensional list of duplicated original faces and a one-dimensional list of the neighbouring faces. So for our first face, which presumably is this one, we have one neighbouring face. Okay, so now we can use some sets components to find out what the shared vertices are and the unshared vertices are. So I'm going to use the discontinuity component to find the corner points of these two faces, and then use some sets components to find the similar members. So for example, we can use a set intersection to find the collection of unique objects present in both sets, which means the objects present in both our original face and in our shared face, which is going to be these shared edges. Okay, so we always get 2 points there, and this is going to be point 1 and point 2. So we'll just use the list item component, pull out point 1 and point 2. Now we can use a set difference, a collection of objects present in A but not in B, to find one of our corner points. So present in our original face but not in the shared face should give us 1 point, which is going to be one of the tips of our triangles, and then present in our shared face but not in our original face will give us the opposite tip. We can leave the strength as 500, rest angle is 0. Actually, I'm going to plug in a slider to control that strength. So that should be enough to create all of our hinge forces, and we can connect those up as a force in our kangaroo physics simulation. Make sure it's flattening data, and you should be able to see what happens when we run the simulation and move some of these corner points. Just have to make sure that's set to false and move the points. We should see, because of our hinge force trying to make the rest angle between all of these plates 0, should see it even out the bending between all of these springs. It's quite interesting. So we're working with kind of like a paper strip model. As we twist the strip, we can also run the risk of inducing some more chaotic hinging. We can control this a little bit by reducing the strength of the hinge force. But essentially what we're simulating here is how a sheet of paper would behave if we were pushing and moving around the endpoints of the strip. Now that we've got the definition set up, we can try it on a more complex mesh. So I've got this disk mesh over here. All we need to do is change our input mesh and also reference in our new anchor points, and then run our simulation again. So in this case, if we move one of the edges, we can start to play around with some slightly more interesting form. Since we've got a more complex sheet trying to distribute these forces. So you could use something like this to begin to generate canopy structures where the angles between all of the plates in the structure would be as much as possible in an equilibrium distribution. Unfortunately, when we're pinning points like this does add some constraints on the structure, so you see that we get kind of peaks where this point's pinned the structure. But generally it will distribute out all of those forces to create something which suggests the form that a real material might take if pinched and pulled in a similar manner.